In section 21, we're going to be looking at exponential and logarithmic equations and techniques that we can use to be able to solve them. The first set of examples that we're going to look at are going to utilize something called the one-to-one property of exponents. This is Theorem 21.1. And I want to start with looking at the second line of the theorem, then we'll go back and look at what the rest of the statement is telling us. It says that if I have a single exponential statement equal to another single exponential statement, and each of these exponential statements have the same base, then the only way that these two statements can truly be equal to each other is if the exponents are also equal to each other. Now that may feel like a trivial statement, that if I'm going to say that two things are equal to each other, then that must mean that everything about them is equal to each other. But it is actually a really important concept for us to think about in terms of solving equations, particularly those that are exponential. Now, the rules for this are that number one, your base has to be an acceptable base for exponential. So in other words, your base has to be positive and it can't be 1. Now your m and your n, as well as your base, all have to be real numbers. Now your base will be a real number because it's going to be greater than 0 and it's not going to be 1. And then your exponents will also need to be real numbers, which is not a problem either. So let's go into example 21.1. It says, find the exact solution of each equation. So I have here part A saying that 3 to the x is equal to 81. Now I understand that many of you viewing this video can just look at this and figure out what the exponent would need to be. 3 to the what power would give me 81. If you know your powers of 3, you can figure this out. But the idea is that I want to get us into this one-to-one property so that way when you get more involved questions and you can't just stare at it and figure it out, you'll have some kind of methodology to be able to get there. So I'm going to leave the left-hand side as 3 to the x. But I'm going to look at 81 and I'm going to view it from a power perspective. 81 is 3 to some power. So when you find the power for that, you'll write it in. The power for this is going to be 4. So according to the one-to-one property, if I have one exponential statement on the left, one exponential statement on the right, and they have the exact same base, then that means that their exponents have to also be equal to each other. So therefore, x would have to be equal to 4. And just like that, you have solved the equation. So you don't really have to do anything with the logarithm here if you understand how to rewrite 81 so that way it has the exact same base as what you have on the left-hand side. So let's see this again with part B. I have 5 raised to the 3x minus 1. That is an exponential statement. But on the right-hand side, I have 125, which is not an exponential statement. It's just an integer. It's a whole number. But it is possible to write 125 as 5 to the third power. And since the left-hand side already has a base 5 with it, I can use this one-to-one property to just set the two exponents equal to each other now. 3x minus 1 is now equal to 3. Then I add 1 to both sides. I get 3x is equal to 4, and then I get x is equal to 4/3. And what amazes me about this particular property is that I started off with an exponential equation. And then after a little bit of creativity in rewriting this statement, I can use this one-to-one property, and now all I have to do is solve a polynomial equation. Specifically, This one is just linear. So all that time we spent earlier in the semester talking about polynomials is going to come back to play here. We can reduce the equation down to just being a polynomial, and then all those concepts would come forward and apply. So that's some good news. There's not a whole lot of new stuff to have to learn here. We just have to understand the creative side of this one-to-one property application. So let's try it one more time here with part C. We have 4 to the x is equal to 32. So if I do the same thing that I've done on part A and part B, then I would leave 4 to the x alone, and I would work on coming up with a way to get 32 written as 4 to the something. Now this presents a problem because, well, 4 to the first power is 4, 4 to the second power is 16, and 4 to the third power is 64. So there is no power of 4 using whole numbers. That's going to give me 32. So what this oftentimes means is that you're going to also have to rewrite the left-hand side. Now on part A and part B, we didn't have to do anything with the left-hand side because the base on each of the original left-hand sides, 3 and 5, those were prime numbers. So it wasn't possible for us to be able to break those down any further. But 4 is not a prime number. So trying to rewrite 32 with a 4 is not going to be the appropriate way to do this. So we're going to nix that idea. But instead, try to think of a base that works for both 4 and 32. So let me erase all this 4 work, and let's think about maybe something else like 2. 2 to the first power is 2. 2 to the second power would be 4. 2 to the third power is 8. 2 to the fourth power is 16, and then 2 to the fifth power is 32. 4 was just too powerful. It wasn't able to give us the right increments to get to 32, but this allows us to not only get 32, but it also allows us to be able to get positive 4. So this is going to rewrite as 2 to the second power raised to the x equals 2 to the fifth. And on the left-hand side, that's a situation where the exponents are supposed to multiply, so we would just call that exponent 2x. And since we have the same base on the left and the right, I can just set the exponents equal. 2x is equal to 5, and then therefore x is equal to 5 halves.